Electron configuration. The Bohr model of the atom, sometimes called the Rutherford-Bohr model, described the atom as a small particle consisting of a very small central positively charged nucleus surrounded by negatively charged particles orbiting around the nucleus, much like the planets revolve around the sun. This is a Bohr model of carbon-12, the most common isotope of carbon. After additional research, the Bohr model of the atom was modified by Schrödinger, the quantum mechanical model of the atom. In the quantum mechanical model, the location and energy of the electrons around the nucleus can be described by three terms: shell, subshell, and orbital. The shell is the distance of the electron from the nucleus, 1 through 7. If you look at the periodic table, you see on the far left 1 through 7. Those are the shells. Orbitals, volume of space around atomic nuclei in which the electrons move. Subshell is a division of a shell. For example, if N is 2, there are two sublevels, 2s and 2p. If N is 3, it would be three sublevels, 3s, 3p, and 3d. There's also x, y, and z. For example, 2p would be 2px, 2py, and 2pz, each of them holding 2 electrons. The s can hold 2 electrons, the p can hold 6, x, y, and z, the d can hold 10, and the f can hold 14. Electron configurations. The arrangement of the outer shell electrons, the valence electrons, provides an explanation for the chemical similarities of elements. Elements having the same number of outer shell electrons, what we call the valence electrons, have similar properties and are placed in groups, vertical columns, on the periodic table. The general order of electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, 4f14, 5s2, 5p6, 5d10, 5f14, 6s2, 6p6, 6d10, 7s2, 7p6. This is the electron configuration for element number 118. A noble gas configuration has a full s and p orbital in the outer shell, the valence electrons, and they are chemically stable. The Pauli exclusion principle. If 2 electrons occupy the same space orbital, one will spin up and one will spin down. The electron configuration for nitrogen is 1s2, 2s2, 2p3. Notice that in the s, which can hold 2 electrons, one spins up and one spins down. Hund's rule says that whenever possible, electrons in the same empty orbitals will spread out. If you look at nitrogen again, the p3s, one goes in the x, one goes in the y, and one goes in the z. They spread out if at all possible. Electron configuration. Hydrogen is on the first level, S shape, so it's 1s1, where the exponent represents 1 electron. It's also the first box. Helium it's on the first level, it has an S shape. It's the only element on the right that has an S shape. All the other elements on the right side of the table are P shapes. It is 1s2, where the 2 exponent represents there are 2 electrons. Lithium, we keep ends of rows and ends of sections. The end of the first row is helium, 1s2. We're going to add to it. Lithium is on the second level, S shape. It's the first box, 2s1. Let's do the electron configuration of carbon. 1s2 is helium. We're going to add to it. 2s2 is beryllium, the end of that section. 2p2. But if you will notice, carbon has a blue hexagon. That means that carbon is an exception. It gives 1 to the S and puts it in the P. So instead of being S2P2, it becomes S1P3. And they give it a particular name, sp3 hybrid. Notice the electrons spread out if they can. Electrons are negatively charged. They repel each other. So if possible, they will spread out. Electron configuration of zinc. 1s2 gets you to helium. 2s2, the end of the first section, second row, is beryllium, 2s2. 2p6 gets you to neon. 3s2 to magnesium. 3p6 to argon. 4s2 to calcium. And then 3d10. Although zinc's on the fourth level, the D's drop back one level, 3d10. And what they do is they write it, they rearrange it to put the D on the third level with all the other third levels. So they rewrite it 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2. Notice that the D can hold 10 electrons. Let's look at the abbreviated form for the electron configuration. Hydrogen is on the first level, S shape, 1 electron, 1s1. Let's look at the abbreviated form for helium. Helium is 1s2. It's on the first level, S shape. Remember, it is the only element on the right side that's an S shape. All of the other elements on the right side are P's. 1s2. Lithium, 1s2 to helium, 2s1. The abbreviated form uses the noble gas that is closest to the target element, in this case lithium, without going past it. Helium is the noble gas closest to lithium without going past it. Helium, in brackets, second level, S shape, 1, first box. Let's look at the abbreviated electron configuration for carbon. Remember, carbon is an exception. Instead of being 1s2, 2s2, 2p2, it takes 1 from the S and gives to the P, so it's 1s2, 2s1, 2p3. You select the noble gas that does not go past carbon. The closest one to it is helium. You put helium in brackets, 2s1, 2p3. Let's look at zinc. The noble gas closest to zinc without going over it is argon. Argon represents 1s2, 2s2, 2p6, 3s2, 3p6. Then past argon would be 4s2, 3d10. They rewrite it to put the 3 before the 4, so the correct abbreviated configuration for zinc would be brackets argon, 3d10, 4s2.